In this video, we're going to look at the kernels of ring homomorphisms a little bit more deeply. So let's prove a property about ideals with regards to homomorphisms. Suppose you have a ring homomorphism between two rings R and S. Suppose that you have an ideal in the codomain, such that the preimage is non-empty. Then the preimage is actually an ideal of R. So remember I stated that you could think of ideals as being the analog of normal subgroups. For group homomorphisms, this was a similar statement we had about normal subgroups. If you had a normal subgroup in the codomain, then its preimage was a normal subgroup in the domain. The only change is that we replaced the word normal subgroup with ideal, and we had to add this extra condition because, of course, actually, now that I'm thinking out loud, you don't need that condition because you're always guaranteed to at least get 0. So, never mind. Alright, so as a corollary of this, the preimage of the trivial ideal must also be an ideal. Notice I'm always talking about ideal as in left ideals, but the same statement's true of right ideals, which means the same statement's true of two-sided ideals. So since the trivial ideal is a two-sided ideal, the kernel is always a two-sided ideal, which is kind of what we discussed last time as our motivation for the notion of ideals in the first place. This is the actual formal proof. It's just going to be a special case of this more general fact. So let's prove this more general fact. So let's take an element in the ring R, and then take an element in the preimage of I. So one thing we already know is that the preimage of I is a subring. So we'll get to that in a moment. Well, I have it down here because you need to know that it's closed under subtraction. But since I is an ideal of S, it's a subring of S, so it's an additive subgroup of the codomain. And back when we were studying groups, this ring homomorphism is also a group homomorphism of the additive group structure. I is now an additive subgroup, so its preimage is also an additive subgroup of R. So that tells us that we're closed under subtraction. And we're non-empty because the preimage of 0 contains at least 0. So the only thing we need to check to claim that this is an ideal is this part. So let's do it. Take an element in R, take an element in the preimage. Then let's compute phi of Rs. Why? Because we want to show that Rs is in the preimage. Since phi is a homomorphism, phi of R times S is equal to phi of R times phi of S. Since I is an ideal and phi of S is in I, by definition of S, we have phi of R times phi of S is an I. So by definition of preimage, since S is in phi inverse of I, phi of S is in I, because I is an ideal, multiplying something by an element in I gives you an element in I. So this product is an element in I. Since this is an equality here, we have phi of R times S as an I, which means R times S is in the preimage. So we have closure under multiplication by elements in R. So we're mostly going to be focusing on this corollary, but it's worth pointing out if you actually go through and study the 4 isomorphism theorems for rings, and you want to understand the full proof of the 4th isomorphism theorem, it definitely relies on this more general fact, because you need to know that you can go back and forth with ideals between the domain and the codomain. However, now we're going to focus on kernels and trying to compute them. So here were some of the ring homomorphisms we've studied already. The first one was complex conjugation. Well, what is the kernel? It's those elements that are mapped to 0. what is the definition of our function here? It takes a complex number a plus bi and it replaces it with a minus bi. So we want a minus bi to be equal to 0. Well, that means the real part has to be 0 and the imaginary part has to be 0, so the kernel is just the trivial ideal. Similarly, we had our homomorphism from z to z mod nz, given by taking an integer and sending it to its congruence class mod n. The kernel consists of those numbers whose congruence class was equal to the congruence class of 0, which means that these are those integers that are divisible by n. So we see that the kernel is nz, multiples of n. Finally, our other homomorphism that we gave was from the ring of polynomials with rational coefficients to the rational numbers, indexed by your favorite rational number. What's this function do? It takes an arbitrary polynomial and it evaluates it at a. So this is called the evaluation homomorphism. So a is fixed and the polynomials vary. What is the kernel? Well, it's those elements in the domain, so polynomials, such that when you apply the map, you get the identity element in the codomain. So those polynomials, such that when you plug in a, you get 0. Now, something you prove in modern algebra 2, and you've learned this in college algebra, but the proof that it works is covered in modern algebra 2, is that the only way that a is a root of a polynomial when a with rational coefficients, when a itself is a rational number, is if you're able to factor your polynomial as x minus a times another rational polynomial q of x. So if you read chapter 17, in case you want to know more about this result, you'll see the full details. This doesn't hold for every polynomial ring, so there's a reason why I picked Q here. Your coefficient ring has to be a field. If it's not a field, this doesn't always work. But in this case, we're okay. And so I had mentioned earlier when we first discussed this example that I was going to show you the better description. Now that we've discussed principal ideals, you can see, well, you're just looking at multiples of this linear factor times other polynomials. So it turns out this kernel is really just the principal ideal generated by the linear polynomial x minus a.